Hi everybody, welcome to your first session of the day. Kind of cool to see so many people, because I know there were a lot of good parties yesterday, right? So myself and Frank and some boys were at the Rubik party, and that was no joke. So cool and amazed to see the lot of you. So today we want to talk to you about host resources, right? And I think we have some nifty, cool stuff for you. Everybody knows the disclaimer, right? So we'll start with a short introduction from our side. I'm Niels Hagoort. I'm a freelance architect, vCDX, vExpert. As of last week, even vExpert, NSX, and vSAN. So pretty happy with that. And you can follow me on my blog or on Twitter. Frank, if you will introduce yourselves.
So my name is Frank Denneman. I'm the technical marketing lead for VMware Cloud and AWS at VMware. And I dabble in resource management on the side. I'm not a vExpert, NSX, and vSAN such as Niels, but I can hold my own on vSAN. So what we have experienced throughout the talks with a lot of customers is that it's not always about high peak performance. If you want to give your customer a good user experience, the best thing to do is to provide a consistent performance or a consistent experience, right? If you have a cluster with old servers and new servers, typically they didn't complain when there were generation 1 servers in the cluster, but the moment you add a second generation and DRS moves it to the new one, you don't get a complaint about, hey, it's really faster, but the moment DRS moves it back, you get a complaint like, what happened? It's really slow, while it was perfect in the first place, right? So that's the same thing with performance on a server and performance in general. And I think a good analogy is the difference between driving in Europe and driving in the US, right? Because in Europe you can drive in many countries faster than the US, but the problem is we have to overtake somebody on the left side, except in England of course. But in the US you actually have the same rules, but you adopted a new rule or an additional rule, and that's keep your lane. So we can drive faster, but sometimes somebody's in our lane and we have to get around it, and that impacts our performance experience. While you can just stay in your lane, and if somebody's actually slower in another lane, it doesn't really affect you, right? You just keep on trucking, and even though you cannot drive as fast as we can, typically you have a shorter drive because it's a consistent flow, right? Now that's the same thing with compute architecture, especially within virtualization, because it isn't only about how is a particular VM configured, it's how is that VM configured and how are the other VMs that are using the same architecture in the server, how are they configured? They can impact your performance, right? So troubleshooting performance is not only focusing on a particular VM, it's also focusing on the rest and how it behaves in comparison or related to the architecture of the computer or the server in general. So the idea is to remove the parts. So basically by keeping your lane, right? So if you can keep it within a particular construct, such as a CPU package or a Numa construct, you don't have the impact of other VMs and their behavior. So let's dive in how this actually works. So when we talk to a lot of customers and we ask about the server configuration, they say, I, for example, have a ESXi host with 20 cores and 512 gigs of memory. What it actually means in today's world is that you typically have 2 CPU packages, and when I say a CPU package, that's actually the thing you hold in your hand, right? So you have a CPU, so on the left side of the diagram, you have one CPU package, and it has a memory controller integrated into it. It uses memory channels to actually address the memory itself. Now in the previous presentation, part number 1, we explained that 3 DIMMs per socket is not always optimal because there are too many components on that channel again, right? Stay in your lane and try to reduce the number of objects in your lane. So the idea is try to keep the DIMMs per channel reduced to 2 at a maximum. So with the new Intel generation that is actually released, that was actually released last month, I believe, right? Yeah. They went away from 3 DIMMs per channel to 2 DIMMs per channel. So they actually removed that problem for you, right? So they are forcing you to use 6 channels instead of 4 channels, but at a lower depth. So 2 DIMMs per channel and now 6 channels wide. Now, the interesting thing is this is one server. So you have another CPU at the other side, and it's connected by an interconnect. Now, if you have a VM running on CPU 0, on the package CPU 0, you can actually access the remote memory as well. But you have to go through the interconnect. And that particular interconnect, that can cause a problem because there can be many VMs that use that interconnect because there can be VMs running on CPU 1 that needs to address memory on CPU 0. Now, the Numa scheduler is designed to keep it as local as possible, but at one point it cannot basically create magic, right? So you have to work with the Numa scheduler. So that means that you have to think about your VM configuration. Wow. So diving in a little bit deeper into the interconnect, I run some tests on particular servers, and this is a server, this is a 2.3 gigahertz version 4 Intel Xeon, and what I saw is that when the Numa node, when the CPU on socket 0 accesses its local memory, so memory node 0, it has an average latency of 75 nanoseconds, right? But if it's actually accessing the memory of the other CPU node, it actually goes to 132 nanoseconds. Now this is an interesting thing, right? So at one point it's still really fast, but the experience is different because if you have a lot of local memory access and now you need to fetch something somewhere else, it will be reduced tremendously, the performance. So you want to keep it local, right? Now this is from a latency perspective, but you also have a bandwidth problem, right? Because there are some bandwidths that you can use in your CPU. So depending on the CPU you actually buy, you can have 6.4 giga transfer per second or 9.6 as the fastest one. Now 38 gigabytes per second is looks really fast or sounds really fast, but if you really test it, you will find out that you actually can roughly get 30 gigabytes per second if you use 9.6 giga transfer per second. Now, again, really fast because a 2400 megahertz DIMM is 19 gigabytes per second, but you're not using 1, you're using 4. So you get almost 80 gigabytes per second. That means if you're local, you can access your memory if you have the memory bandwidth of almost 80 gigs. If you go over the interconnect, it will reduce tremendously, right? Now, and that's even if you have just one VM, but you have multiple VMs, right? So it will actually be reduced. Now let's dig in a little bit deeper even more. So what I draw here was the two CPUs that you saw with the CPU 1 and the CPU 0 and the CPU 1. This is the internals of a Xeon, basically a logical sketch of it. So you have your cores, the black squares, and the light squares in the middle are actually the cache environment. So the design of the CPU is actually that the last level cache is inclusive. That means that it will always appear in that cache. Now, if you look at the path of data, in the worst case scenario, you go from memory to the CPU register. So storage, memory, cache, register, and then it's being processed in the CPU itself. That means that everything will go through the cache. and everything of all the CPUs will go through that cache. Now that means that there can be multiple CPUs that actually use that bit of data. So it has to check which one is the latest version, because otherwise you can get data corruption or something else. So what you want to do is you want to keep that as the footprint as small as possible. So you want to contain that into a single CPU. Now, the Numa scheduler of ESX actually tries to do that. And we have actually, we have a lot of experience by troubleshooting that one for a large telco customer, because what we do is we do something, or the Numa scheduler does something like action affinity. So in this test, we started 2 VMs. And due to the round robin process of the Numa scheduler, it will start up the first VM on Numa node 0 and the other one on Numa node 1. So try to balance it. In general, it will do that all the time, except when there is a 5% load difference, right? If one CPU is loaded more than 5% or utilized more than 5%, it will start to schedule on the other CPU until that difference is less than 5%. Now what happened is that these 2 VMs on home node 0 and home node 1, they started to communicate with each other. They started to communicate at the memory level. So they were sharing the same type of memory. They were sharing the same type of data that happened to be in the cache. So Numa actually understands that, and they say, okay, it's really important to keep everything as compact as possible, because now I only have to look inside of one area instead of going over to the interconnect and asking where is that memory located in your other cache, right? So what happens is they start to actually, or the Numa scheduler starts to move it to a single Numa node. So it will try to reduce the moving parts again. It will try to avoid using the interconnect. Now this sounds brilliant, but if for the untrained eye, you say, hey, my system is unbalanced because all, in this case, my workload is situated on node 1, and we have 36% of load, while my other CPU has 0, right? So this is something worth to actually troubleshoot. So if you see some weird stuff happening from a load balancing perspective, this might be the case. Now, in most of the time, this is actually a good thing, but in certain cases, it can be a terrible thing. Now, there is an advanced setting that allows you to change that behavior, but it's a host setting. So the default weight of local affinity is 130. If somebody can tell me what that 130 is, I would be a very happy person, but I've never ever found somebody who could tell that to me. I do know how to fix that, or basically change that, is by setting it to 0. At that point, we don't consider affinity, we don't look at the behavior between the VMs on the same system, right? So be careful with this, but it might help you in certain cases. This is one of the optimizations that happens in the Numa scheduler, right? So another one, and I think you're familiar with it, is virtual Numa. If I look at my blog and if I look at what is the highest search request, it's always virtual Numa, and it's virtual socket. So I thought, let's discuss this. So if you look at, from a logical perspective, scheduling, CPU scheduling on a ESX host, you will have vCPUs. And so we go from top to bottom. So you have a VM, you configure the number of CPUs. There's actually an additional setting that's called cores per socket. Typically it's set by 1, and that's the default, but in some cases, or for some companies, they use a different standard, and they will say, my standard is 2 cores per socket. Now, that socket, that vSocket, that impacts the scheduling abilities, because we are influencing the logical constructs of the schedulers, right? That is the vCPU grouping. Those are the Numa clients, and I will dig into a little bit deeper. Now, the Numa clients are a affinity group for the CPU, such as same as a VM to VM affinity group, we do that with CPU sockets. So the moment you have a Numa client with an X number of virtual CPUs, they will be scheduled on a physical CPU. That's the grouping, right? If that entire Numa client is on a heavy utilized CPU, it will be moved entirely. So in that case, if you look at the top level, if the one on the left is experiencing a lot of delay, that single CPU, vCPU, will be transferred to another Numa node. Or the other might be even a better fit because you will impact the load balance even more. So those two vCPUs, a member of a particular VM, will be moved over to another CPU inside the same host. So that's the role of a Numa client. It's basically helping the Numa scheduler to figure out what to move where. Now, then we have the actual CPU scheduling, and that's done by the CPU scheduler itself. So you have a Numa scheduler that basically tells the CPU scheduler what to do, or basically give them hints. What you typically see in all the documentations is there's what we call a P CPU. Now, P looks to basically, is always explained as physical CPU, but that's not entirely true. But that P CPU can actually be scheduled on a core, so the second on the right, or it can be scheduled on a hyperthread. You cannot control that whatsoever. Now, what happens is, if you are scheduled on a hyperthread, you will experience some delay because you have to share your local caching of your CPU. So we will reduce the amount of time we will charge you for scheduling. So if a CPU is scheduled on the core itself, it will be charged 100% of the time of that CPU. If you are scheduled on a hyperthread, you will be charged 62.5% most of the time of CPU time. That means that you will have some rebate left, so you will be scheduled again, right? So you will get the same amount of CPU time, but it's over a longer period of time. So that can cause latency as well, right? Now, one of the most difficult myths to bust is actually, when does vNuma kick in? Now, vNuma, what we mean by vNuma is actually exposing the Numa architecture to the guest OS and its application to optimize for itself. Now, vNuma is only exposed when you exceed 8 vCPUs, and now here comes the defining moment, and whether the vCPU count exceeds the core count of the physical CPU itself. So in this configuration, or in this test, I have a 10-core CPU. Now, I installed, or I configured a VM with 10 CPUs, 10 virtual CPUs, and I still have one Numa node. I'm still not going to expose the Numa configuration because there's nothing to optimize, because you have one element, one thing to schedule on. So the VPD, that stands for Virtual Proximity Domain, and that's something is the virtual Numa that we expose to the guest OS itself. So what I did is I increased the number of CPUs to 16, so that will exceed 10 physical cores. And now you will see that we will have 8 virtual CPUs in one VPD, VPD 0 to be exact, and you have the other 8 in VPD 1. So what Numa Schedule does, it will evenly balance the virtual CPUs across the minimum number of virtual Numa clients. So now you have 2 virtual Numa environments that we will expose to the guest OS. So it can do its own Numa scheduling, such as Windows and such as Linux-based machines. By default, the default configuration of a VM means that you have one CPU, one virtual CPU with one virtual socket. Now, it's a really weird situation, actually, because you picture this from a physical perspective. You have a main board, and now you have 8 virtuals, now you have 8 sockets. That's weird, but that's the way we emulated the environment. So we will ignore the virtual socket because it's default, and we will create one virtual proximity domain. That is the Numa client, and that it's matched to the physical proximity domain. Now those 8 vCPUs can be scheduled on the 10 physical cores of the CPU, right? Now we have the same thing on the other end as well. But what happens if you say, I want to have 2 cores per socket? You will get a VPD per vSocket because it's a non-default configuration. Now you think, okay, I have more constructs to load balance, so that's actually a better thing. Well, yes and no, because at one point there's just a limited amount of places to be actually scheduled. The real thing is that we are exposing this to the application and to the guest OS itself. So what happens is that you will have, again, a lot of virtual proximity domains, but if you look at this from a guest OS perspective, and this is MS Core that's run inside a Windows machine, you will see that there are now 8 Numa nodes. And what Windows will do is will say, okay, these Numa nodes have their own local memory. So we have a particular cost relative to the fastest cost. So what will happen if I need to fetch memory from another virtual socket? Well, in reality, it's actually on the same physical CPU. So that's not an optimal situation. You're basically micromanaging the whole thing, actually in a very bad way. Why didn't it work? Okay. So one thing that we want to recommend is if you go and use virtual socket, a non-default configuration, try to mimic the physical part as much as possible. So if you have 10 cores, right, say, and you want to have 16 vCPUs, and you have 2 physical Numa nodes, configure the VM with 8 virtual CPUs per socket. Now, I know that this isn't always the case because there are some licensing problems, right? But if that's not the case and you want to have the ultimate best performance, try to mimic the physical parts as much as possible. Why? Because what will happen is it will see that it actually has a unified cache. So that part on the left side, those 8 CPUs will actually share its cache. So by the idea of the guest OS, of course. So you will get the optimization in the most optimal way that aligns with the physical parts, right? Now, in some cases, you have a memory-intensive environment, and you have provided a X number of CPUs, but it doesn't fit inside a Numa node. But it's because it's more memory-intensive instead of CPU. What you can do is you can use prefer HT. That's a setting which can be on a virtual machine level and on a host machine level. So what you do with this, you will force the Numa scheduler to count actually the hyperthreads instead of cores, right? So what I had with 16 vCPUs, if I set it, if I just use the default, when it comes to 10, well, it counts it to 10, then it breaks it up. When you do prefer HT, now I have 20 elements to use. So it will actually restrict the number of Numa nodes or Numa clients. So in this case, you will see that the node 0 actually has a VM that has 16 vCPUs, while I only have 10 physical cores, right? So that allows you to confine it in a particular Numa node. Now this can be helpful from a memory perspective, but if you are also a CPU, if you're running a CPU intensive workload, this might not be the best solution. So again, be careful with this, but this is something that might help you solve some of the most difficult problems, resource management problems to cover. Now, what if you have a VM that actually can fit inside the CPU from a vCPU perspective, but not from a memory footprint? So if I have a 8 CPU VM on a 10-core system, but I have 96 gigs worth of memory, and the Numa node only contains 64 gigs, we need to fetch it somewhere, right? So 32 gigs will automatically be remote access, because we need to schedule it somewhere. What happens is the Numa scheduler is fixed and focused on the number of vCPUs, not on memory. So the Numa client itself will always be configured on the count of virtual CPUs. So there's a setting which is called Numa consolidate, and what will happen is it will break it up in the minimum number of Numa clients. So in this case, it will actually create 2 Numa clients with each a X amount of memory. So you will have more local memory compared to the other situation. Again, very advanced setting, so don't use it lightly, but it can help to solve some of your resource problems. Now we advertise this session as CPU, storage, and network, so let's go over to storage a little bit. Does anybody know in the room what one I/O cost from a CPU cycle perspective? Shout it out. I heard 20,000 somewhere over there. Exactly, you read the book, right? So on a local device, when we want to create one I/O, it actually takes 27,000 I/O cycles. That is a lot, right? So you have the holy grail of 1 million IOPS in most of the marketing material. So that actually we need to have 27 billion cycles in your system. I see a lot of home lab posts complain about flash devices that they cannot really get to the best performance, and then when you look at the CPU perspective of the CPU configuration of that home machine, it just have 4 CPUs or even less, right? So yeah, your flash device can actually create or can actually deliver a million IOPS, but you just don't have the raw power. So when you calculate this and you have 10 cores running at 2.2 gigs, you actually need to have 13 cores to actually push a million IOPS in one box. Now, the industry looked at that and they said, okay, let's reduce the moving parts again. So they came up with, this is one of the devices that can actually provide a 1 million IOPS in your local box, right? Now, the industry looked at it and they said, okay, what's the problem? And the problem is there are so many layers inside the storage stack, and each of that stack will need CPU cycles, right? So with NVMe, they reduced the storage stack. Now you only need 9,000 or a little bit above 9,000 for one I/O. If you calculate that, you only need to have 4 cores now. So by using a different storage stack, you can actually, a software stack, you can actually reduce the number of CPU cycles. Those other cycles can be used for other VMs, right? So again, if one VM is pushing a lot of I/O, it doesn't interfere with the other ones because you have a lot CPUs left. So from a diagram perspective, on the right side, you will see SAS, which is a little bit more efficient than the traditional one, almost 20,000 cycles. On the left, you will see the software stack of NVMe. A lot less moving parts, right? Now, recently, Intel announced the new type of memory, 3D XPoint, and they are using a different type of stack as well, right? They're still using NVMe, but they optimized it as well. This is from a time perspective, and this is microseconds. So they are trying to optimize not even at nanoseconds, but at microseconds. So what you will see here is the difference between just your regular flash and what future NVMe is actually the Optane or the 3D XPoint environment. Now 3D XPoint is different from flash that it is bit addressable, right? So now you don't have to, when you write something, you don't need to erase a full block, so all that data doesn't need to be moved to somewhere else and all that stuff. There are plenty of storage sessions at VMworld that actually explains this in greater detail. But the key thing to understand for Optane or 3D Crosspoint is that it only needs to have a low queue depth to actually perform at its best level. So the interesting thing is, if you look at the specs of a Intel Optane device, is you will see that it can only support up to 16 I/O from a queue depth perspective. Now if you look at the test from normal flash, you will see that they always push a high queue depth, 128 or whatever, because that's where the parallelism shines from a flash perspective. That's not the case with the new 3D Crosspoint. So you will see that because it's beta addressable on the right side, you will see that the performance, and I don't think you can read it very well, so please look at the slides when you come back home, is that you will see there is no impact of the operations of other I/Os on the device, right? Stay in your lane, reduce the moving parts again. So the blue one is actually the performance line of flash, actually experiencing additional load. The brown line is actually the performance throughout the load of a Optane device. So where is this used for, right? When do you choose Optane versus flash? Now with vSAN, you have a cache tier and a capacity tier. So for the caching tier, 3D Crosspoint is excellent because you have a low queue depth, where you have the best performance with a low queue depth, because you just, sometimes, not every VM is pushing a lot of I/O all the time, but they want to have a fast response. They want to have the best performance with the least amount of I/Os. So 3D Crosspoint is the perfect way to allow for the caching tier. Because you're pushing a lot of sequential writes to your capacity tier, that's where flash shines, right? Because there's a lot of parallelism inside the device. So for that particular reason, I don't think you actually want to use 3D Crosspoint, because nowadays the capacity is not there yet, but the overall SQL performance is incredible from normal flash, right? So think about that. If you're in the process of designing a new vSAN environment, think about this, right? I think that's my part. So, Niels?
Thank you, Frank.
Oh.
Everybody still sharp?
Sorry.
There was a lot of info, man. So, I want to take it a little bit further from a CPU utilization and a latency point of view, coming from the perspective of networking. And the truth is, nowadays we all accept latency in our data center, and nobody likes latency, right? It's what users experience as an application or workload being laggy. They're complaining to you guys, and we don't want that. But we do accept it, because we do not want to spend that many CPU cycles on it. It's all about the performance versus capacity and consolidation ratios. So looking at this, well, really simple mind map, it is the question if your workload needs to be latency sensitive, or is latency sensitive, or it is not, and you will thrive more with the CPU savings and have a larger consolidation ratio. Now for 80, maybe 90% of the workloads out there, the CPU savings part will probably be the best option, because you will be able to fit more workloads on your physical service. But there are certain workloads that actually require the lowest possible latency. So an example is NFV workloads, network functions virtualization, and that's really a movement which is gaining traction right now with the old telco industry, moving to 5G, the Internet of Things, workloads like that. So an example of that is an enhanced packet core, for example. Then you'll have an EPC node that is the packet gateway, and it is traversing a lot of network I/O. You do not want to see latency on that workload. Another workload example is maybe SAP HANA or other transactional workloads pushing out a lot of network I/O. And the thing is, as said, we all accept latency, because CPU savings is probably the way to go for typical IT applications. So this is what actually is happening in your ESX host nowadays. So we are talking interrupts. And an interrupt is actually a message from incoming packets. And an interrupt is processed and handed over to the CPU and tell the CPU process these packets, right? So what happens if network I/O packets are received by the ESXi host? They will actually be buffered, right? So you have the first packet arrival, packet 2, up to a certain point, and then an interrupt will be generated. And that's the moment when the packet is actually being processed. So think of it as stepping into a train and you really want to move fast, you're in a hurry, and you still have to wait for the train to get full of people, and then it eventually takes off. So one of the mechanisms that is enabled by default actually is interrupt correlation. Other mechanisms, and we will discuss that a little bit further on, are ring buffers. But interrupt correlation is actually an interesting thing. So that is actually the mechanism, if you're NIC supported, and every modern NIC nowadays does, it will actually buffer, right? And using this command, this ESXCLI commandlet, you will actually see what is happening for a specific physical NIC. Now, we are talking microseconds here, right? So is it even noticeable? It all depends, as always, right? It depends on your network I/O pressure, and if you see this to a higher value, you might want to consider tuning it. And looking even further into this setting, and you'll have the VSI shell. For those not familiar with the VSI shell, it is really a bomb of information. There's a lot of metrics out there. So in this actual VSI namespace, you'll see the RxQ correlation stats. And interesting to see is that you have a queue depth of 64. So that's, as with the storage stack, are the network packets that can be handled in parallel. But the second highlight is actually the RxQ length. Again, it's a value of 64 right now. And that is actually the metric that defines that 64 packets needs to be received before generating that interrupt. So that's the latency part you are introducing in your ESXi host. So as just mentioned, the other one is, and there are a lot of more out there, but ring buffers. And ring buffers actually come into play when you are receiving a large burst of network I/O. And again, we have an ESXCLI command which shows us what is actually going on from a receiving point of view per VM NIC, so the physical NIC. And we see that the value is set to this. Interesting thing about ring buffers is if you are flooding your ring buffers because you are receiving a large amount of network I/O, it is perfectly possible that packets are being dropped. And that's an interesting thing, right? So ESXstop, I think you're all familiar with ESXstop. It has this value, right? The drop packets Rx value. And what I saw in multiple cases is that metric is actually presented as 0. So that would mean, yeah, we're all good and no packets are being dropped. But again, VSI shell to the rescue if you really want to see what's going on the background. So digging into VSI shell, we have this very long command, and it will show you for a specific VNIC if the actual ring buffers are full and how many times that has happened. So you see here that, yeah, well, the value should be 0 or close to 0, but it is not. So we needed to dig in even deeper, and with another VSI shell commandlet. And when you see this is actually interesting, because here we see a lot of dropped Rx packets, right? Over 8,000. And, oh, well, even 80,000. So this is what to believe, right? ESXstop is that's probably an average, is a percentage-based value. But if you dig deeper, you actually see that there is a lot of drop packets out there. Now, well, to overcome that, you will you will actually be able to increase the ring buffers. This knowledge base article states how it's done. It's primarily a guest OS setting. But it can be solved, right? So that was the CPU savings part, right? These are all functionalities and features that allow for a CPU efficient network environment. But now let's look at the latency side. So if we have those workloads who require the lowest possible latency. And that's where polling actually comes into play. So on the other end, we have the interrupt based driver model, which we just discussed. And the poll mode driver model is actually, well, it's not that often used. On the other end, Frank just told us about NVMe. And NVMe is a poll mode driver, right? And the big difference between them is that a interrupt waits for the packets and then sends an interrupt for the packets to be processed by the CPU. A poll mode driver model is actually a driver that is polling a queue, and whenever a I/O comes in that queue, it will get processed immediately, hence the lower latency. So telcos nowadays tend to use DPTK, which is a poll mode driver. That's an Intel data plane development kit driver, and it's actually living inside a Linux OS nowadays. And that allows you that the application is able to directly interact with the network stack in ESX. What will be interesting to see if we will ever see a poll mode driver in the actual vSwitch stack, right? So you can bring it down a level. But for now, today, the poll mode driver for network I/O is done with DPTK. So if you bring that all together, you will see on the left-hand side the CPU savings part, right? So you are saving on CPU cycles, and you will be able to have a higher consolidation ratio at the cost of latency, because latency will increase. So again, is that noticeable for your workload? Yes, no? That's, well, up to the workload, right? On the right-hand side, you will see the poll mode driver version, if you will. So you have the lowest possible latency at the cost of CPU cycles. Because with DPTK, as just discussed, you will have a VM and you will actually assign vCPUs to the DPTK driver. And each vCPU which is assigned to the DPTK driver, it will consume every CPU time or cycle you will give it. So yeah, you're not looking for consolidation ratios, you're looking for the lowest possible latency. So about latency and performance, let's bring it back. There are a lot of tunables in ESXi, right? But also the choice for virtual hardware. So if you want to have the lowest possible CPU overhead and possibly the best performance, you will look to have a direct access from the VM to the physical NIC. Now, SER-IOV, is there anybody using SER-IOV actually? I didn't think so. Oh, I saw somebody. So it has its use cases, right? But it comes at the cost of the vSphere features that are not usable when using it. And what you are really doing, you are actually creating VFs, virtual functions, on a physical NIC, and you assign those virtual functions to a VM. And using this, you will actually skip the ESXi kernel for direct access to the physical NIC. Direct I/O is another way of doing that, but that's really a one-to-one relationship. So you'll have one virtual NIC and one physical NIC, and those are directly connected to each other with no other VMs able to use that physical NIC. It is used for storage solutions though. But as just said, you will probably need that from a CPU savings perspective or a performance perspective. Thing is, we tested it, and it's still a discussion on internet. A search on E1000E versus VMX Net3 versus SER-IOV. there are a lot of tests out there. But this is our own test, and what we saw is that the bars are actually the throughput, and you have 2 lines for receiving and transmitting CPU utilization. And if you see it, the VMXNet3 driver and the SER IOV, well, there is practically not a difference between them, right? So VMXNet3 looks to be the way to go, even if you want the lowest possible latency. Because when using VMXNet3, you can still use VMware, vMotion, and features like that. But luckily, we have some innovation on the ESXi side, and we are now using or able to use direct access to memory. So as of vSphere 6.5, we actually have virtual remote direct memory access, virtual RDMA. And using that, you will be able to communicate between VMs, between workloads, if you will, using direct memory access, right? So virtual RDMA, it kind of looks like this. These are the constructs. And on the left side, you will see the traditional network stack, if you will. So you have the buffers in the application, the whole TCP stack, IPv4, all the way down to the network device. And below you'll have the actual physical network, right? So virtual RDMA, once the control path is set up, you will completely trespass skip the ESXi kernel. And that is interesting, right? And you will be using high transport networks like iWarp, RDMA over converged Ethernet, and that is actually the only one supported in vSphere 6.5 today. But we will see more innovation on that part. So you will be able not to use the traditional driver stacks as just discussed, but virtual RDMA. So from memory blocks in one ESXi host, one VM, to another ESXi host using RDMA over converged Ethernet. And there is actually a session going on at VMworld. I don't know if it's already done, but you should look it back. It's a use case of virtual RDMA for extreme vMotion performance. So that's actually a pretty interesting innovation, and well, we'll see a lot more from that. And on that note, all the content we just discussed is in our book. It is available on Amazon, but on-prem we have our bookstore and the rubric stand, which is actually given away, the host resources deep dive book.
Sorry to interrupt. Actually, rubric, is my mic on? Can you hear me?
Yeah,
okay,
cool.
So rubric gave away 1,000 copies, but they're already, they did it in one day. So.
Oh yeah. They're already gone, so you're out of luck.
Sorry, we couldn't control that. So the only one is actually at the bookstore, but it's also available on Amazon, on your local Amazon, or actually on ebook version as well, if you prefer that.
Exactly. So we have some time left if there are any questions.
So the best question will get one of those, right? I think we have a mic, so please walk up to the mic for a question.
Where do you see a mic?
Hey guys.
Yeah.
Oh, there you go. The bright light.
To achieve those benefits with ESXi, what changes are there any requirements for the VMs, such as like hardware versions or VMware tools that need to be at certain levels?
You said you started off with ESXi. What do you mean?
To achieve all these benefits.
Which all benefits? What we just
yeah,
discussed?
Everything you discussed.
Okay, so we based all this stuff on the recent version of 6.5. So
right,
that's the first step to upgrade your ESXi host to 6.5.
Okay.
And then basically go on from that.
So if we migrate our infrastructure over, the VMs themselves,
yeah,
would they have to be a certain level of hardware version and VMware tools?
Well, as Frank said, we're always tested with the latest version of the hardware tools, or the hardware version.
So I believe virtual RDMA needs to have the latest version.
Okay.
Right? Yeah.
Cool.
Thanks.
Thank you.
If you have some workloads that are configured with like 16 sockets today and a single core. Is it worth taking the time to move those to like 2 sockets, 8 cores each?
So in general, the way vSphere works and the way we created the CPU scheduler and the Numa scheduler, it works very well for most of the use cases. So there's no need to actually tinker with those things. But if you want to squeeze out the last bit of performance, then it might help, right? Especially exposing the cache, the unified cache at a virtual machine level. That is one of these large percentage performance increases. So it's up to you whether you want to have that operational overhead or not, right? But in general, you can throw everything at an ESX IOs and it will perform pretty well, right? It's amazing. We've seen some configurations that we thought like, this won't work. Then when we tested, like, it does work, right? So optimization is, I should only optimize when you actually need it, because you have other things to do as well, right? All day long, so, right? So, optimize when possible, when needed. Yep.
Gotcha. Thank you.
Thanks.
There's some over here.
Are you guys going to have to make any changes to the Numa scheduler with the new Intel Scalable? Because now you don't have that ring anymore. You've got more of a matrix, more cache locality per core.
So we are exposed to production examples, right? So when Intel is releasing new stuff, we get to see it pretty much first. So we work with them as well, and we figure out what we needed to actually change to do. But most of the time they run on a particular scheme, an x86 scheme with extensions. So we can just plug into that without changing most of our code. So in general, you can drop the new processor in a 6.5 box and it just works.
So you didn't have to make any optimizations for local cache code?
Nope.
Affinity, okay.
So the ring is interesting for caching perspective from their part, not from ours, right?
Okay.
So
no page table changes or nothing, any?
Not as we know of, as today, right? But maybe we see an optimization down the road that we think, hey, that's a very interesting thing. When you look at cluster on die, that is also different, which is multiple Numa nodes in a CPU. That could be interesting. Maybe we need to change something about that. But typically, from the caching perspective, no, we don't need to. Cool. Yeah, good question.
Hello. If you make these changes to your host, does it matter how you build your clusters in vCenter? Is vCenter smart enough to know that one host has one optimization versus another when it's scheduling, or should you keep all birds of a feather together here?
So vCenter is not involved in any host scheduling at all.
So it's up to us to put them all in the same cluster?
Yeah.
Yeah, okay.
So from a configuration consistency perspective, yeah, that's all down to you.
Okay.
Yeah?
So you can use tools such as vRealize to figure stuff out, but overall it's just basically keep things together, keep it similar as much as possible.
Makes sense,
Yeah,
thanks.
Question. In the past, when you turned on hot CPU add, it disabled virtual Numa.
Correct.
Does that still happen in 6.5?
It is different now. There are some caveats, but that's too complex to address right now. But there is, we have some knowledge base articles on it. Right?
Thank you.
Thanks.
I'm curious if you guys have any recommendations on RSS in the guest. We've had some issues with clustered exchange where RSS actually played a role in a lot of dropped packets.
Oh yeah, so RSS is actually something we discussed in the session last year. And wow, yeah, we have a lot of recommendations. They are actually in the book. So there are a lot of drawbacks or drawbacks.
I think he stumped you. So.
Huh? Yeah? Yeah, okay. You will get it.
Thank you.
So come pick it up and we'll discuss after, right? Cool. Do we have another one? We have
one more.
Yeah, one more.
RDMA, will that make a big difference to vSAN?
Well, sorry, come again?
RDMA, the network, will that make a big difference to vSAN?
Wow. So now, as far as I know, it's not usable for vSAN just yet. And that's primarily because of the fact, and I didn't mention that in the session, you are bound by only one It's a virtual network adapter, right? So, and you are bound to a limitation of one virtual network adapter per VM right now. And yeah, that's not assignable for vSAN as far as I know. So, but in the future, well, maybe, would be interesting. Yeah.
I'm trying to understand what performance can be squeezed out by having 1 core per socket versus 2 cores per socket. I understand if the machine is small enough, it's still going to fit on the same Numa node. But as far as trying to understand it on an extra cache or some sort of level, I've failed to be able to understand what that benefit is of 1 core to 2 core using 6.5.
Exactly. So it doesn't, right? So sockets, virtual sockets within a Numa node doesn't have any performance effect at all. That's only when you want to use it for a licensing perspective. If you use virtual machines that have virtual Numa, basically exceeding a single CPU socket, that's where vSockets might help you with squeezing out extra performance, because then it allows you to transfer that knowledge to the guest OS, right? So it can then start to optimize. But if you contain it within a Numa node, there are no performance benefit for vSockets, right?
Understood. One more question, please. When I was reading your book, I had trouble understanding some of the cost benefits of using hyper-threading. I see it's somewhat controversial. Yeah. But if we go ahead and take the leap and we can't afford to shut down the entire production environment, would it be okay to have one host at a time with hyper-threading on, with the rest of them off, while we gradually shift them all to hyper-threading, and then the same with Turbo Boost? Because we're concerned about having half the hosts with hyper-threading and half the hosts not with hyper-threading, and we don't want to have to take everybody offline to do it.
So why did you turn hyper-threading off?
That was already off, and that was something that we discovered. And it's been very difficult to come up with an argument to turn hyper-threading back on, because it's a very controversial topic.
Okay, so I would recommend to turn it on, because the CPU scheduler has this time cost calculation. I logged it on my site, frankdenneman.nl. So look at CPU scheduler and reservations. That's what the article title is. There I explain how actually the CPU scheduler works from a time allocation perspective. So because the CPU scheduler is aware that that VM or that vCPU shares the CPU constructs within that CPU itself with another CPU, with another load, it will reduce the number of charged time, right? Like I said, 62.5 in most of the cases. That means that it has been allocated 100%, but it was only able to use 62.5%. So basically we're in debt to that VM, right? So we will get it again. Typically, that latency of being scheduled twice, so a longer period of time to actually get the stuff done, you won't see a performance impact on most of the workloads. So now, instead of having 10 scheduling possibilities, no HD on a 10-core system, you have 20, right? So now it can actually start to distribute a lot better the workload around it. So by having 20 options. Right, so you understand it, right?
Yes,
so,
yes.
Okay. So by turning it off, it only has 10. So you start to add latency as well, because now workloads are actually in the queue.
And I know in your book you explain, like you just said, that ends up paying back whatever it missed from that 40 or so percent. But as far as having half of them and hyper-threading on or off at the same time, is that our concern? We weren't able to predict the impact of putting one into maintenance mode.
Well, just run a test, or maybe one of the tests we like to use is DVD store, and where you can see it processed a number of operations. So you run that test on a machine with hyper-threading off and with on. But here's the catch. Run it with multiple workloads, right? So if you do it on an empty box, there's not going to be a difference, right? So you have to mimic, you have to do it like in a normal operation. So try to keep the host as full as possible, use the consolidation ratio you typically use, and then run that test. Then see what workload will perform better. I will ensure you that the HD one will perform better, right? So I think, we have 30 seconds left. So I think go back, enable it, it will help you, it will get better performance.
Thank you.
Overall, yeah. So thanks for coming and have a good show.
Yep.